we are sort of poised at a turning point, an inflection point, I suppose, between our examination of phenomena, that is to say, electricity, and then magnetism. We have these two sort of disciplines, areas of inquiry, historically, that we have intimately related to each other. We've talked about induction and how a changing electric field manifests a magnetic response, and vice versa. So we're sort of confronted on the one hand, I suppose, or confronted with the consequences of that. And that's what the next module on Canvas is called, is our our model has consequences. So what does it mean that electricity and magnetism are so closely related? And what can we do with that? It is sort of mind-boggling to regard the rapid end of the semester. It all feels like it's rushing to a close. It makes me think in this particular moment about something I remember from my music theory classes. And as far as classical musical composition is concerned, a composer will spend a whole movement moving slowly between different sort of chord structures and tonalities, and then at the end, progressions between chords are compressed in time, and it seems like change happens fairly rapidly, and on a certain level, that's kind of what we're doing with the different topics. If you're following along in Young and Friedman, Thursday this coming and Tuesday next is a big pile of chapters. Like it's like 4 chapters that we're talking about on those 2 days. Partly because the distinctions between the 2 chapters are, in my opinion, a little bit fluid. But just because I think it was important to spend the time early in the semester really exploring those motifs that we're using to sort of tell this story, to write this piece of music, the piece of music that is electricity and magnetism and what they do for us. So if things feel like they're sort of moving quickly here at the end, that's okay. It's in a way supposed to feel that way, and in a lot of ways, it mirrors the history of the science that we're dealing with. We spent, I don't know, 200 years before having a significant breakthrough in the study of magnetism. And in a matter of what we talked about, 30 years, 50 years, 70 years, everything had exploded sort of conceptually. So we're sort of mimicking that in a way. wave equation. The wave equation is, in fact, where we left off. We were talking about the description of a sinusoidal traveling wave in space. We ended up with that thing in a box with the minus sign if we are propagating to the right, a plus sign if we are propagating to the left. And we took derivatives. In this case, we took them of the right, in the x direction, a rightward propagating function, but we would end up with the same overall result if we had used the plus sign. We took two partial derivatives with respect to time, holding place constant. And we took two derivatives with respect to space, holding time constant. And the relationship between them is that they are scalar multiples of each other. In terms of the wave speed. And that's not something we made up. That's a physical certainty having to do with the, I've got it here. Having to do with the time derivative of the phase of this traveling disturbance. So this is no trivial result. This is a very meaningful thing. That a traveling sinusoidal periodic disturbance is sort of intimately related to itself. In space and time, like is related across space and time by its own propagating speed, which I think makes a certain amount of sense to say that out loud. But it didn't come from our sort of first chapter of physics 231 kind of understanding that displacement over time is speed. This is something maybe more fundamental than that. Remember, y in this case, y is a function that expresses the amplitude, the displacement from equilibrium, as a function of space and time. And at a given place and time, the rate at which its displacement from equilibrium's rate is changing. It's because it's the second derivative, right? The rate of change of the rate of change with respect to time think about the motion up and down of a mass on a spring. The acceleration in the 231 sense, second derivative of vertical position with respect to time, is intimately related. Now, partial y with respect to x, now we're thinking about like a Cartesian xy, and we think about this, the shape of the medium carrying the disturbance. Partial y with respect to x is the slope. It's the curvature of that spatial relationship. And the acceleration in time, the curvature in time is related to the curvature in space according to the wave equation. So if, for example, we were able to show that for some other function of space and time, that the curvature in time of that function, in this case smiley face, is a scalar multiple of the curvature of that function in space. That function represents a traveling wave fully in the sense that we were talking about here. Let's see what this does for us. We'll have a better appreciation, I think, for the applicability of this statement later if we can probe the application of it to a mechanical wave. Suppose we have a wave on a string, or a slinky, I suppose. So a sinusoidal transverse wave such that the motion of the string at any point is vertical, perpendicular to the propagation direction along the string. We have this oscillation that's propagating along the stream. With what speed does it propagate? Now, any sort of experience with a stringed musical instrument of any kind means that we know that the more we ratchet the tuning knob, the tighter the string becomes, the higher the pitch. Now that's very subjective. That has to do with our perception of the phenomenon of frequency. But we can see this with, it doesn't have to be a musical instrument. We can talk about the change in the auditory response as I change the tension in the rubber band. So something about the frequency with which the thing vibrates, and therefore the pitch that we hear, something about that behavior has to do with how taut the vibrating member is. What is the tension in the rubber band and in a string that is propagating some sort of sinusoidal disturbance? As you might expect, if I found a thinner rubber band, a narrower string, I get a different response. And if you examine the strings on a violin or a guitar, you know that the string that vibrates at lower, that sounds with lowest pitch is the thickest of the strings. So we have two sort of empirical parameters that we're manipulating here: the tension in the string and the heaviness of the string. It's size, I guess, but they're all the same length. So it's not, because it's an instrument, right? It's not just that the size of the strings is different. It's that the thickness, the heaviness, the weight per length, I suppose, is different. So we're considering the tension force and the mass per unit length, which I can call mu for now. Suppose we zoom in. On a section of the shape of the string. Actually, I'd like to zoom in a little bit farther, really resolve this picture. And we asked about the tension in the string. Now, tension in the string, there's a tension acting along the string this way. And it's the same string, so the same tension exists acting here this way, let's say. But there are different components. I mean, we're interested in the vertical oscillation of these points of mass. So we have the vertical component. And the horizontal component. And these two points are made a distance apart from each other. Let's label it this way. One is made at x, and the other is made at x plus delta x along the x-axis. The curvature, well, I guess not the curvature, but the slope, the secant evaluated at x is related to the vertical component at x over partial y, partial x. We could label this F, I don't know, F1, the first point, I suppose. F1 of y, or F1 sub y. What do you think about this claim? Actually, I don't think I like this claim. It should be y over x. I mean, it's a slope, right? dy dx, we're talking about a slope. We're explicitly talking about at a point in time. So we're saying partial with respect to x, but we're just talking about the physical slope of this shape. We have this string subject to a horizontal tension, not one that is, depends on the, I don't think these two magnitudes are the same. These two red vectors, I think I have to mark them different. What is true, what is the same from x to delta x is the horizontal tension. I mean, otherwise, we wouldn't be talking about sinusoidal motion in the first place. It has to be the case that the farther displaced we are from equilibrium, the more the spring medium tries to pull us back. That's the whole point of a restoring force in oscillation. It has to be the case that the farther away we are, the larger the vertical force, the larger the force at all. So I think I got to label this FT1 and FT2, but what we can keep the same, oops, are the horizontal tensions. Now, the slope at FT1, that's negative because it's down and to the left. If we write the same relationship at the other point, we get a different result. What is the net vertical force on this section of string? Just the sum of the two. Now, this sigma f notation, it's on purpose because it makes us think about F equals ma. What's the mass of that green highlighted segment of string? Well, it has to do with the mass per length. How much length are we talking? Well, it's the delta x between the 2 points. So that mass is the linear mass density mu times the linear space delta x. That mass times the acceleration should be the net force. And the horizontal forces cancel. So the net force acting on this part of the string is right here. It's what we just wrote. So this had better be equal to mass times acceleration. Now, acceleration is the time derivative. But we got to write it as partial, but it's the second time derivative of the position. When we see this, that's ma. All right, so we can rearrange this a little bit. Divide both sides by delta x, divide both sides by f. You might be curious how we were able to talk about the 2 points, one side and the other side, with as though in the green ink that they have the same acceleration. Or I guess we're talking about the acceleration altogether of that chunk of string. But I guess the left side and the right side are experiencing different accelerations. So the only way I can really feel good about writing what I just wrote is if there really isn't any distinction between the left side and the right side of this little green highlighted chunk of string. In other words, let's bring those 2 points closer and closer together. But what is this thing on the left-hand side here? By definition.
A derivative.
Yeah, it's a derivative of the function del y del x. And if we compare that thing I just wrote to the wave equation, we can see that mu over f is the square of 1 over v. It's the reciprocal, because it used to be on the x side. So if we put it on the x side, well, we're saying this now, f over mu, and that means that compare this to the wave equation. Okay, that means y is a traveling wave, traveling with wave speed. The tension in the string divided by the mass per length density, which is exactly the two things that we said we have observed different response from.
I have a question. Why would it be F subscript T?
Well, it's actually F. Just letter F, the horizontal tension to which we have subjected the string. I just put the T back to talk about the fact that it's a tension.
Mm-hmm. Okay.
Yeah. The total tension experienced as a function of time by each point along the string is not necessarily equal to F. This is the horizontal tension. Yep. The letter F without a subscript makes me feel all like all lost and confused. What kind of force is it? So that's habit. We could use a similar analysis to ascertain the rate at which a wave of this sort transfers energy from one spot to another. Recall that the instantaneous power if we follow the definition, I guess was defined as a small amount of work done over a small amount of time. Now, a small amount of work done would be a small force times a displacement, or a force times a small displacement. Technically a dot product. But that dx dt is velocity. So we should be able to calculate the power transmitted by a wave of this sort as the force times the velocity. It's a dot product, so we need these to be in the same direction. The per particle motion is vertical. So it's the vertical force we're interested in, and the vertical speed. You might already be able to see where I'm going. Looking back at this picture, at any given spot, the force, the vertical force, is the negative of the slope. The physical slope, right? If the physical slope is positive, then the string is pulling back. That's what we're showing here. I suppose we need the net. The net vertical force. Which does have to do with the curvature of the net vertical force is the tension times the curvature. I'm looking at this in the limit as delta x goes to 0. That's the horizontal tension force times the spatial curvature. Velocity is much easier. That's the time derivative. So what do we end up with if we run with this? And I think by the time we're done, we will have a means to argue that this minus sign, which is the minus sign that was kind of throwing me a little bit, is the way it needs to be. Let's chase the consequences. The partial y with respect to x, we have written here, it's negative Ka sine kx minus omega t. The partial y with respect to t, we have written here, it's omega a sine kx minus omega t. So if we multiply them, negative k omega a squared sine squared where I left the minus sign out front, the minus sign that I'm curious about. The thing is, power needs to be positive. We're sending energy at a, we're not, what would negative power even mean? I really want this to be positive, which means I need that multiplication to happen. A negative transfer of energy? I mean, I suppose power could be if we're doing negative work, but we are moving energy along the string with the force of tension in the string itself. That's what pulls the stuff, the disturbance along. The force of tension pulls and it travels in that direction. That's positive power as far as I'm concerned. So I really want that minus sign. You could find zeros in the instantaneous power. Sine squared does have zeros. Oops, I forgot the F. dy dx is here, dy dt is here, but I forgot the F. Now, the tension force F is related to the speed of propagation according to that thing we just found. So we could express this in terms of the physical parameters. Suppose we were interested in the average value in time, I suppose. This is a squared sinusoid. We know what it looks like. Halfway between maximum and zero. The maximum is just what we get when sine squared is equal to 1. And the average is half of that. We saw this trick back when we were talking about AC current and the root mean square current and potential difference. The power was, yeah. So the average power it's just that. Wait a minute. Hold on. I gotta go back. Oh yeah. No, I'm okay. My bad. This is fine. If you're following along in Young and Friedman, this doesn't quite line up with what they have, but that's because I didn't express things in terms of mu, the linear mass density. This is perfectly fine. If we wanted to put mu in there, we know that the tension force is related to the propagation speed and the mass, the linear mass density. All right, let me write that down. We said that V was equal to a couple different things. We said that it was equal to, for a particular string, the horizontal tension divided by the linear mass density. We also said that it was equal to omega over K. So here where we have F, we could replace that as V squared mu. Or see, but then we've got K and omega. Omega now wait a minute. V squared is omega over K. So I think F, all right, is equal to, hold on, V squared mu, but V squared is equal to omega over K. That's going to be relevant in a little bit. So one more thing I'm going to talk about from the waves chapter. And that is, what happens if we send a wave along a string and it hits a wall? Like the string is fixed at that end. So we've got our wave coming. And as it propagates, the tension in the string is going to try to pull up on that point, which means that point, that fixed point, is going to, has to, Newton's third law, is going to pull back the other way. And it's fixed, you can't move. So it's going to pull the incoming wave down. And what will happen as the propagation comes at this fixed point, and we saw this, I think, in the video that I took in slow motion on my phone, that it'll flip upside down and propagate back the other way. Because that energy has to go somewhere. And if it can't propagate into the wall, it's going to turn around and come back on the string. With the upside down reflection that has to do with Newton's third law. So in this case, we've got a right going and a left going periodic disturbance of the same phase, just with one's upside down. What is the result of two propagating disturbances? Well, it's a force, right? This is all just forces. It's tension forces. So if you have multiple forces acting on a given point in the string, we just add them all up. What that means is that the solution is just we add them all up. What we've got is a right-going wave with some amplitude. I just want to match what we set up here. I'm going to stay with it. It was a cosine. Kx minus omega t. And we also have a left-going deal of opposite polarity. Left going, so we use the plus sign in the argument, and it's of opposite polarity, so we include minus sign. What happens if we add these two things? Let's call them y1 and y2. Now, who remembers the identity for the cosine of a sum or difference? We got cosine of a plus b is, I think, cosine, cosine minus sine, sine. And if we include the minus sign, it's a plus. Almost positive. So this is a times. If we split up kx and omega t, this is kx minus omega t, so that's cosine, cosine, cosine omega t. With a minus sign, so this we get a plus, sine kx sine omega t, plus negative a times, same story, but now cosine kx cosine omega t minus sine kx sine omega t. I think this term and this term are going to cancel because one of them is multiplied by a, one of them is multiplied by negative a. And I think this term and this term are going to add because the negative sign is going to be multiplied by the negative a. So I think we're going to end up with a sine kx sine omega t. But notice that this isn't a traveling argument anymore. I can't put this back in terms of, not cleanly, in terms of a kx minus omega t. We've sort of separated the x and the t relationship. There's no phase velocity to talk about anymore.
Would it not be 2 times that amount?
It would.
Okay.
They do, in fact, add. You're right. But here's the thing. Consider just this piece. Think of this like a spatially modulated amplitude. So if it's an amplitude, we could have the opposite. And sine omega t, there's our time dependence. So our string along here oscillates between two amplitudes. But at this point, oscillates with no amplitude. Because the function that multiplies sine omega t is 0 there. The x, the spatial dependence of this thing, isn't time varying. We've separated them. The spatial dependence, the curvature of this thing, is what it is. It's fixed. There's still oscillation in time, right? We still have a sinusoidal, each point on the string moves with some amplitude, but that amplitude is shaped by the spatial dependence. This point only oscillates with that amplitude as opposed to the larger one. And some points oscillate with no amplitude. This looks to us like an oscillation spread over a length. So it looks like a wave that doesn't travel. It just stays put. Mostly because it's sloshing back and forth between two walls. But what it looks like to us is a series of these node and antinodes. This is going to be relevant for us shortly. We call this a standing wave. And it is the relationship in space of the standing wave to the physical parameters of the system. In other words, where we have to be fixed here and fixed here. And if we are so fixed, they have to be nodes. That we've nailed that spot to this particular y coordinate. It can't oscillate. Has to be a spot of 0 amplitude, which means only certain wavelengths, only certain spatial stories will fit in this deal. K, remember, is related to the spatial period, how many cycles per space. We have only certain, only discrete values of k that will work for this physical situation. In this case, we are showing the case where the space we have is 1, 2, 3. 3 spatial cycles, 3 wavelengths. There are other modes, other possible forms for other values k could have. We could have just one big antinode, and that's the longest possible wavelength that is possible with 2 fixed ends. Or we could have 2 antinodes, or we could have 3 antinodes. But the point is, there are only certain wavelengths that are stable, capable of standing sort of until the energy dissipates. And those wavelengths, now remember, wave speed, frequency, and wavelength are related. So if there are only certain wavelengths that are stable in this physical space, that means for a given wave speed, which is only determined by the medium and how much tension we exerted on it, different wavelengths will manifest as different frequencies. Has to be. And if the frequency is what we hear as pitch, this helps explain why we hear different pitches from a guitar strings. We're subjecting them to different tension and different linear mass density, which means that each string has a different characteristic wave speed. They're all the same length and they're fixed at the ends, so the wavelengths on each one are actually the same, but because the wave speeds are different, the frequency profile is different. This story of nodes and antinodes, like I said, is going to be relevant here in just a second.